All right, so you sent over this paper called Functional Risk Minimization by Fan Alley and some folks from MIT. And
yeah,
I gotta say, just looking at it, it's pretty intimidating, all these equations and
yeah,
really dense concepts. So that's why you're here to help us unpack this.
absolutely happy to be here.
So we've got the paper itself, and we've got some analyses and explainers and that sort of thing to help guide us through this deep dive. And I guess the fundamental question that I keep coming back to is, why does machine learning still rely so heavily on this idea of empirical risk minimization, or ERM?
That's a great question, and it's a good place to start because ERM has been the workhorse of machine learning for decades. You know, it's pretty simple in principle. You just find a function that minimizes errors on your training data and hope it generalizes well to new unseen data.
So it's like finding the best fit line through a bunch of points on a graph.
Yeah, exactly. It's like finding the best fit line. But the paper really highlights a crucial limitation of ERM, and that is it works under the assumption that there's one single true function that can perfectly explain all the data.
Right, but that's...
In reality, things are far more complex.
Yeah, the real world is messy, and so trying to force fit everything into one neat function that might not.
Yeah, that's right. And as data sets become more massive and models become more complex, the limitations of ERM become even more apparent.
Yeah.
So this paper is arguing that instead of focusing on finding the perfect output for every single data point, we should shift our attention to the functions themselves.
Yeah, interesting. So instead of asking, did the algorithm predict the right answer, we're asking, did it learn the right way?
That's a great way to put it, yeah.
To approach the problem.
That's the core of functional risk minimization, or FRM.
Okay.
It suggests that each data point might arise from its own unique function. Sampled from a distribution of possible functions, they call this functional generative models, or FGMs.
Wait, so each data point having its own function. Can you give me a real-world example to illustrate this?
Absolutely. So let's say you're building a model to predict house prices based on features like size, location, and age.
Right.
ERM would look for a single function that tries to capture the average price for houses with similar features.
Okay, so like a general rule of thumb for estimating.
Yeah, like a general rule of thumb. But in reality, there are always variations that a single function can't fully explain. Maybe one house has a particularly beautiful garden that drives up its price, or another was sold below market value due to unique circumstances.
So those variations aren't just random noise, they reflect the unique stories behind each.
Exactly, and that's what FRM tries to capture. Instead of seeking a single average function, it considers a distribution of functions, each reflecting the unique factors influencing a particular data point.
This is fascinating. So how does FRM actually work? How do we shift from minimizing errors in the output to minimizing differences between functions?
So mathematically, the paper derives an objective for FRM that minimizes the difference between two probability distributions.
Okay.
But here's where it gets a bit abstract in function space, not output space.
Okay, I'm sensing we need to unpack that for our listeners.
Sure.
What exactly do we mean by function space and probability distributions?
Yeah, so imagine a vast landscape where every point represents a slightly different function instead of searching for a single peak representing the best solution. We're considering a cloud of possibilities, a probability distribution centered around the ideal function.
So instead of finding a needle in a haystack, we're mapping out the haystack.
That's a great analogy. Now, the challenge is, how do you actually compute? With these probability distributions over functions, it gets computationally intense very quickly.
That makes sense. So did the authors come up with any clever ways to make this FRM objective practically computable?
Yeah. Here's where their ingenuity shines. They offer two approaches first for complex models like large language models.
Okay.
They propose a variational approach. Instead of modeling variations across the entire massive model, they focus on what they call the adaptation space, which are the specific parts of the model that are fine-tuned for a given task.
So it's like zooming in on the most relevant parts of the model instead of trying to map the whole thing.
Exactly. The second approach, designed for more general deep learning models, uses what's called a Taylor approximation.
Okay.
This leverages the fact that these models often have way more parameters than data points.
Right.
And uses some clever mathematical tricks to simplify the problem.
All right. I'm getting a sense of the mathematical gymnastics happening here. But the big question is, does FRM actually deliver?
That's the million-dollar question.
Does it outperform good old ERM?
That's what we'll explore next.
Mm-hmm.
The paper dives into experiments across various domains like linear regression, reinforcement learning, and variational autoencoders, and the results are quite compelling.
Let's dive into those results. Where did FRM really shine compared to ERM?
Well, in linear regression, they found that FRM excelled when the noise in the data was what we call heteroscedastic.
Okay.
Meaning the noise levels vary across different input values. Think about real-world scenarios. Noise is rarely uniform.
Right. It's more like unpredictable bursts of static rather than a consistent hum.
Exactly. And in those cases, FRM consistently outperformed ERM. Now, they also applied FRM to reinforcement learning, where an agent learns to make decisions in an environment.
Like a self-driving car navigating a city.
Precisely. They found that when the information the agent received about the environment was incomplete or biased, FRM was far superior to ERM in learning the task effectively.
So FRM seems to be much more robust to imperfections in the data, almost like it's learning to think critically.
That's a great way to put it.
About the information it's receiving.
And finally, they looked at variational autoencoders, which are all about learning efficient representations of data.
Okay.
They found that FRM led to better representations, especially when the data had the kind of structured variations we see in real-world data, like variations in color or position.
It seems like a recurring theme here is that FRM really shines when dealing with the complexities and nuances of real-world data.
You hit the nail on the head.
Where those neat, idealized assumptions of ERM start to break down.
And that brings us back to the bigger picture. Why should you, the listener, care about FRM? This isn't just about tweaking algorithms.
Right.
It's about a potential paradigm shift in how we approach machine learning.
This is definitely getting me excited about the future of AI.
Yeah.
We've covered a lot of ground in this first part of our deep dive into FRM, but there's so much more to explore.
Absolutely.
I'm eager to hear more about the practical application
We'll get into that.
of this revolutionary approach.
In the next part of our deep dive, but before we move on, let's take a moment to reflect on the core concepts.
Okay.
We've discussed so far, and maybe you, the listener, have some initial thoughts or questions brewing. So welcome back to our deep dive into functional risk minimization, as we were discussing before the break. This shift from output-focused learning to function-focused learning has some really profound implications.
It's almost like we're moving from teaching machines to memorize answers to teaching them to think, wouldn't you say?
That's a great way to put it. Yeah, it's not just about improving performance on benchmarks. It's about changing the very nature of how machines learn.
Exactly. And that shift in perspective opens up a whole new world of possibilities, especially when we start thinking about specific applications.
Right.
So let's dive into those applications. What are some areas where FRM could really make a difference?
Well, one area that immediately comes to mind is medical diagnosis. Imagine a world where instead of relying on vast data sets of labeled medical images, we could train algorithms to understand the underlying biological processes that give rise to those images.
So instead of just recognizing patterns, the algorithms would be able to reason about the causes of those patterns.
Precisely. Think about diagnosing a condition like cancer. There can be so much variability in how the disease manifests in different patients with ERM. You'd need massive amounts of data to capture all those variations, but with FRM, you could potentially train algorithms to understand the underlying mechanisms of tumor growth metastasis and response to treatment.
That would be a game changer. You could potentially diagnose cancer earlier and with much greater accuracy, even in cases where the visual signs are subtle or ambiguous.
Yes, and this principle applies to countless other medical conditions as well. FRM could help us develop algorithms that are more sensitive to individual variations in physiology, genetics, and lifestyle, leading to more personalized and effective healthcare.
That's incredible. It makes you wonder, what about other fields, for example? I know a lot of our listeners are interested in the future of AI, especially when it comes to things like natural language understanding and generation. Could FRM play a role there?
Absolutely. With ERM, language models are essentially trained to mimic patterns in text without truly understanding the underlying meaning or intent.
So they're like parrots repeating phrases without grasping the concepts behind them.
That's a good analogy, but with FRM, we could potentially train language models to understand the underlying structure of language itself, the grammar, the syntax, the semantics.
So instead of just predicting the next word in a sentence, they'd be able to actually understand the meaning of the sentence.
Yes, and that would lead to AI assistants that can truly comprehend and respond to our requests, chatbots that can hold meaningful conversations, and even systems that can generate creative text formats like poems or scripts that are not just grammatically correct, but also emotionally resonant and contextually appropriate.
Now, that's what I call a truly intelligent machine.
And let's not forget about self-driving cars. They rely heavily on perception systems that can interpret the environment. And those systems are typically trained using ERM, but the real world is a chaotic and unpredictable place, which can throw ERM-based systems for a loop.
So a self-driving car trained on a data set of perfectly sunny days in California might freak out if it encounters a snowstorm in Boston.
Exactly, but with FRM, you could potentially train these perception systems to understand the underlying physics of the world, how objects move, how light interacts with surfaces, how weather conditions affect visibility.
So self-driving car would be less reliant on memorizing specific scenarios and more capable of adapting to novel situations in real time.
Yes, and that would make self-driving cars much safer and more reliable, even in those edge cases that ERM-based systems struggle with.
This is all incredibly exciting stuff, but I also want to acknowledge that this is all still very theoretical. We're talking about the potential of FRM, but we're also dealing with some very real challenges, like those computational costs we discussed earlier.
That's an important point. FRM is still in its early stages, and there's a lot of research and development needed before it becomes a mainstream approach.
So what are some of the key hurdles that need to be overcome?
Well, as we mentioned before, computational efficiency is a major one. Finding ways to approximate those complex calculations is crucial, especially if we want to apply FRM to those massive state-of-the-art models that are pushing the boundaries of AI today.
So it sounds like there's a need for more efficient algorithms and potentially even specialized hardware designed specifically for FRM.
Absolutely. And another challenge is data. FRM requires a different way of thinking about data collection and annotation. Instead of just labeling outputs, we need to find ways to capture those underlying functions that generate the data.
So it's not just about quantity of data anymore, it's about the quality and the way the data is structured.
Exactly, and that might require developing new tools and techniques for data annotation and potentially even rethinking how we design experiments and collect data in the first place.
It seems like FRM is forcing us to rethink a lot of the assumptions we've been making of machine learning for years.
That's the beauty of truly innovative research. It challenges the status quo and pushes us to explore uncharted territory. And who knows, maybe FRM will be the key to unlocking the next generation of truly intelligent machines, capable of not just mimicking patterns, but actually understanding the world around them.
That's a fascinating thought before we get too far ahead of ourselves. I think it's helpful to take a step back and revisit some of the core concepts of FRM, just to make sure we're all on the same page. Join us for part 3, where we'll do just that and delve a bit deeper into the theoretical foundations of this research. Welcome back to our deep dive.
Yeah.
I feel like we've really gone through a lot.
Yeah, we've covered a lot of ground.
Exploring, this exciting new frontier in machine learning.
It is exciting.
From, the limitations of traditional ERM to the core ideas behind FRM, and even a glimpse into potential real-world applications.
Mm-hmm.
But before we wrap up, I think it's valuable to revisit some of those
definitely
core concepts just to make sure
a little recap.
We're all on the same page.
Yeah.
So let's solidify that foundation.
Okay.
At the heart of FRM is this idea of functional generative models, or FGMs.
Right.
Can you remind us what exactly FGMs are and why they're so important for this?
Yeah, so FGMs challenge a fundamental assumption of traditional machine learning.
Okay.
And that is the assumption that there is a single true function.
Mm-hmm.
Perfectly explaining the relationship between inputs and outputs.
Right.
Instead, FGMs propose that each data point might arise from its own unique function, sampled from a distribution of possible functions.
So it's like acknowledging that the world is messy.
Exactly.
There isn't always one neat answer.
That's right.
To every problem.
And that's where the generative aspect comes in.
Okay.
FGMs don't just try to fit a function to the data. Mm-hmm. They try to model the process that generated the data in the first place.
I'm starting to see how this connects to the idea of functional noise. It's not just random errors.
Right.
The output. It's variations in the underlying functions themselves.
Exactly. Think of it this way. If you're trying to model the price of a house based on its size, location, and other features, traditional ERM would look for a single function that predicts the price as accurately as possible.
Like finding an average price for houses with those features.
Right. But with FRM, you'd consider that there might be subtle variations in the market, perhaps due to things like buyer preferences, negotiation skills, or even just random fluctuations.
So instead of looking for the average price, You're acknowledging that there's a range of possible prices.
Exactly.
Influenced by factors that are hard to measure directly.
Precisely. And by modeling this functional noise, FRM can potentially capture those nuances and make more accurate predictions, especially in those edge cases where ERM might falter.
This is really making it click for me now. I remember us talking about how FRM is particularly well suited for over-parameterized models, which are so prevalent in deep learning today.
Can you
elaborate on that connection?
Of course, over-parameterization essentially means having more parameters in your model than data points to fit.
Right.
It might seem counterintuitive, but it's a key reason why deep learning has been so successful. It allows these models to capture incredibly complex patterns, but it also makes them more susceptible to overfitting, which is where ERM can run into trouble.
So it's like having a powerful engine.
Yes.
But not quite knowing how to control it.
That's a great analogy. FFRM offers a potential solution.
Okay.
Remember how we talked about FRM essentially assigning each data point its own function? Well, in the context of over-parameterized models, this can be seen as a form of regularization.
Regularization. That's a word we haven't mentioned yet. Can you explain what that means in this context?
Regularization is a way of preventing models from becoming too complex and overfitting the training data, in the case of FRM, by encouraging the model to find a set of functions that are all relatively close to each other. It prevents those functions from becoming too wild and overfitting individual data points.
So it's like finding a balance between flexibility and control.
FRM allows those over-parameterized models to flex their muscles, so to speak,
Right.
but it also keeps them on a tight leash, preventing them from running off into the weeds of overfitting.
That makes a lot of sense.
Yeah.
We've talked a lot about the theoretical side of FRM.
Yeah.
But I'm curious about the practical side. What are some of the challenges in implementing FRM?
Yeah, good question. So, as we've discussed, computational cost is the biggest hurdle.
Okay.
Dealing with probability distributions over functions is computationally demanding, especially with larger models and data sets.
So all those high-level mathematical gymnastics come at a price.
Indeed, but researchers are actively developing more efficient algorithms and approximation techniques. For example, the Taylor approximation we mentioned earlier simplifies those complex calculations by making some clever assumptions about the function.
And the variational approach, especially for those massive language models, how does that help with the computational cost?
The variational approach approximates a complex probability distribution with a simpler one in FRM. This allows us to focus on a smaller subset of the model's parameters, making the computations more manageable.
So it's like finding a shortcut through a dense mathematical forest.
Exactly. As researchers continue exploring these approaches, FRM becomes more practical, paving the way for wider adoption.
This has been an incredible deep dive.
Right.
We've gone from the theoretical foundations of FRM to its potential to reshape industries and technologies as we wrap up. I want to leave our listeners with this thought. FRM is more than just a new algorithm. It's a fundamental shift in how we think about machine learning. It's about moving beyond pattern recognition towards a deeper understanding of the processes generating the data we observe. This shift in perspective has the potential to unlock a whole new world of possibilities, from more accurate medical diagnoses to safer self-driving cars to even more human-like artificial intelligence.
I couldn't agree more. FRM is still in its early stages, but it holds immense potential to revolutionize machine learning and reshape our world.
So to our listeners, stay curious, keep exploring, and who knows, maybe you'll be the one to make the next breakthrough in functional machine learning. This has been The Deep Dive, and we'll see you next time.